Hi everyone, so this is the seventh and final video of the Heap series, and in this video we are going to talk about heap sort. Now, heap sort was actually the basis of why we started talking about heaps to begin with, so this is a pretty important topic. And what we want to do is we want to actually take a look at how we can actually take our heaps that we've been talking about for the last few videos and using that to actually sort. Okay, so our basic, here's an array, sort this array from small to big or big to small or whatever. That idea, how do you use a heap to do it? Now, heap sort is actually pretty straightforward in terms of what you want to do. You want to start by taking the array of values and building a heap out of it. And then once you've built the heap, you're going to dismantle the array one value at a time. And what you will get out of it is a sorted array. And the reason for that is because remember, when we do a removal, we remove based on priority. So we actually take out the numbers that we remove based on their priority. Highest priority is removed first, second highest is removed second, third highest is removed third. So if we think of our values as priority values, what we get is we get our values from highest to lowest priority. And that's how we do our sorting. So the algorithm is build a heap, dismantle it one value at a time, and record the values that are removed every time we do a removal. So let's start with that idea first, okay? Now, this is the heap that we got using make heap in the previous video. This is the last thing that we got out of it. So now what we're going to do is we're going to do make heap on this particular array. Sorry, we've already done make heap. We're going to actually remove the values just to sort of observe what will happen to this. So let's do it. So when we remove a value, the first number that is removed is the number 1 because it's at the root, right? So we remove it. So the equivalent on the array. We find a new home for 7, okay? So 7 right now is sort of floating off in somewhere. Now, at this point, actually, before we start, let's talk about what happens. So right now, we can think of the entire array, the whole thing currently is a heap. Okay, like every single number here is part of the heap. Now, when we start removing things, okay, what happens is our heap actually isn't as big as it was. We've removed a value. So right now, our heap actually starts at like element 0 and only goes to element 6. So the rest of it isn't part of the heap at all. Now, why is this important? Well, we'll see in a moment. So anyhow, I removed the number 1, and I have to find a new spot for 7. 7 can't go at the root, so we're going to move the 2 up because that's the higher priority child. So 2 gets moved to the root. I can't put 7 in the empty spot because 7 is bigger than both 5 and 6. So again, we move the smaller value up. Okay, so equivalent. Now, can I put the 7 there? Well, it's a leaf node, so sure. So I'm going to take the 7 and move it into the node over here. Same thing, 7 gets put into the array. Okay. Now, just to quick reminder, remember our array is effectively these nodes, right? So they are, so the node actually is in a certain index. So positionally, they equate to the array. So the first number that came out of the array is the number 1. Now, if I do it again, okay, same algorithm again, I remove another value, what will happen next? Well, the 2 is erased. So let's erase it. And I'm going to find a new home for this number 6 right now. So the 6 over here at the bottom, I have to find a new home for it because it's no longer in the right place. I have to find a new home for 6. Okay. Now, what it means is that if I think about it in terms of our array, the array is actually now only the first 6 elements, 0 to element 5. And I have to find a new home for this. The 2 got removed, so as long as I record that the fact that it was removed, we're fine. Okay. Now, can I put 6 at the root? The answer is no. It's lower priority than both, um, 3 and 5. So we're going to move the higher priority child up. Okay, so 3 becomes the root. Okay, I put 6 into the empty spot. Still no, because it's lower priority than 4. It's higher priority than 8 though. So 4 comes up. And now, can I put the 6 in? The answer is yes. So 6 ends up here. Okay. Now I've removed 2 values from my heap. Now, let's do one last removal, one more time. Okay. So again, I do a remove. And what that means is the 3 comes off the heap. Okay. Record that. And I am now moving the heap. I have to find a new home for number 7. So effectively, my heap is actually only in this part of the array. The 7 actually is not part of uh, my heap anymore, where the 7 was, I mean, element 5. So let's find a new home for 7. Where do I want to put it? I can't put it at the root because it's lower priority than 4 and 5. So I move the lower priority child up. Okay, that's the 4. Take the 4, move it to the root. Can I put the 7 in there? The answer is still no, because 6 is higher priority than 7. So 6 moves up, and 7 is placed in. And there we go. So we've got a heap. Now, here is what we have. So every time I do a remove, I get another number, and my heap sort of shrinks down as I go. Now, great, I'm getting sorted numbers, 1, 2, 3, 4, 5, just like I normally do. And obviously the next one that will come out will be 4. The problem is I don't have a place to put these right now. So obviously I can make a second array. I can copy the things in. But then Heapsort doesn't solve the problem of not using extra memory. Remember, we already have an n log n, a guaranteed n log n algorithm in merge sort. Okay? Merge sort is n log n. Doesn't matter how you get the data, always n log n. The biggest problem with it was that you had to have a second array. So if memory was sort of constricted and you don't want to double your data size, merge sort was sort of bad because it required a second array to do the merging. Quicksort is faster than merge sort, but in some sort of like cases where you constantly pick a bad pivot, and by the way, it's constantly picking a bad pivot. If you pick only one bad pivot, it's okay. It's just one extra iteration through the entire array. It's when every single time you pick a pivot, you manage to pick the worst pivot you can pick. That's when it degenerates to n squared. So you don't. So that's. But quicksort does have a possibility that your runtime is n squared. So Heapsort sort of avoids that kind of probability and also doesn't require a second array. But obviously, if I'm pulling these numbers out, I I have to have a place to put them. I can't just like leave, like I mean in the picture, it's like on the whiteboard somewhere. But in memory, you need a place for them. The unfortunate part is that the way that we're doing it right now, we don't have a place to put the numbers we pull off. Now, as I was drawing this, what you will notice is that we actually made space. Look at how our array is. What part is the heap? Our heap does not require the entire array all the time. Every time we take a number out, we open up space. The thing though is that the space that we open up is at the back of the array because that's where the bottom rightmost node is, right? So as we take numbers out of the array, we actually open up the array in the back of it. But we can't put 1, 2, 3 there because obviously 1 came out first. This spot was available, then 2, then 3. What we would end up with is we would end up sorting in the wrong direction. We would end up with the smallest at the back and the biggest at the front, right? Because we open it up that way and we remove based on, a min heap. So how do we solve this? The answer is actually really straightforward. All we need to do for heap sort okay? And this is the one thing to remember, okay? To sort from smallest to biggest, okay, we must build and dismantle a max heap. Higher values have higher priority. The highest value has the highest priority, okay? Um, so this is really important. We actually have to do it opposite to the way that we think. The one number that we want to take out first is the absolute biggest, because what it means is that when we take it out, we have a place for it because we just opened up that last element in the array, that last element where we used to be part of the heap. We don't need that to be part of a heap anymore. We can just put our number in there. So this is why when we're doing heap sort, we actually want to do it opposite to the way that we want to sort. So if we want to sort from smallest to biggest, we want a max heap because we want to take out the biggest number first, because that's the one that goes at the back. That's the first opening we have when we dismantle our heap. Okay, so that's pretty much so to avoid this problem, what do? Build max heap instead, not min heap. Okay, so that's sort of the key. Build a max heap, not a min heap, and you will have this. So let's very quickly take a look at an example. So here's a non-heap, okay? 8 numbers, not a heap. So let's turn this into a max heap very quickly. So I want you to pause the video right now and call make heap on this array and see if you actually get the same one. Okay, so pause the video and do a make heap on this. I'll give you 5. Okay, 5, 4, 3, 2, 1. Okay, so hopefully at this point you've paused the video, you've turned it, you've made a heap with it. Now I'm going to do it. I'm going to show you how to do it. I'm going to do it relatively quickly. So let's do this. So make heap begins by starting over here. So remember, we're going to do this by making a max heap. We're not doing a min heap this time because we're going to be sorting with this. So max heap, how do we build it in place? Well, we start with this node right here, number 2. Why? This is the first non-leaf node if we started by going backwards, right, to how we built the nodes. Okay, so we started by going to the left, and then we go as far as we can go until we find the first non-leaf node, which is the number 2. So is this correctly heapified? Is this a proper heap? The answer is no. So what do? We swap the 2 and the 4. So 4 and 2 in our array, 4 and 2. Okay. Now, next, we work our way backwards. Is this a proper heap? Nope, not on a max heap. So again, we take the 1, we swap it with the higher priority child. Remember, it's a max heap, so the higher priority child is 7. So we're going to swap the 1 and the 7 here. 7 and 1. Excuse me. 7 and 1. Okay, next, we're going to swap. We're going to look at the number before that. Okay, so remember what we're doing is we're just kind of working our way backwards in the array. So in terms of coding, remember that this is these are array elements, right? So we started at element 3, and we're just kind of going backwards in the array. So this is like when you're coding it, it's just like a loop backwards, okay? So now we look at number 3. Is this a proper heap? No. So again, compare it to its children, pull up, swap it with the higher priority child. So that'll be the 8 and the 3. What color? 8 and 3 here. Okay. Now, so 8 and a 3. And now, is this a proper heap? Right there. And the answer is yes, because it's a leaf node. So we're perfectly fine and happy there. Let's leave it alone. So now we do it again. Okay. So what do we have? um, 8 and 5, compare those. Or sorry, not 8 and 5. Um, we take the 5 and we try to put it into the heap. Can we do it? And the answer is no. So swap 5 and 8 because they're not correctly ordered. So 8, oops, 5 and 8. So 5 is here, 8 is here. Now, is this a proper heap? And the answer is yes, it's a proper max heap, so we don't have to do anything more. So here we do 5, we have 5, we have 8, and then we have 5, and you can see this is now a proper max heap. No one said this thing is sorted. It is just a max heap. Now, so what do we do next? Well, to sort, we now have to do multiple removes, okay? So let's do 3 of them. So I want you to remove the 8 and draw the heap as you go. How does this open up our heap? So currently, the entire array, the whole array is considered a heap. This whole thing is a heap right now, okay? What happens if you do one removal operation? So pause the video, 5 seconds, remove the biggest item from this heap. Okay, remove, just the remove we've been talking about. Okay, so pause, go. 5, 4, 3, 2, 1. All right, so let's see what we can do. So I'm going to remove the biggest number from the heap. Now, there's different ways to do this, but if you're going to actually do a sort, the easiest is actually just to do a simple swap. Put the 2 here, put the 8 here. Now, why do you do that? Well, remember that this 8 is no longer part of the array, right? So effectively, the heap only goes up to that point at this point. This is 8. This part of the array is now sorted. Okay, so this is sorted array is from where the heap is all the way to the end. Now, all we really need to do is actually put 2 into the right place, right? So if 2 is actually in there, we can just call heapify, because remember the rest of our, like this is actually a heap, and so is this. So we actually have 2 heaps. We just have to make sure that the 2 is in the right place. So what do? Okay, so again, compare who is the higher priority child, which is 7. So 7 goes to the root, and 2 is now here. Okay, so we swap these guys, 7 and 2. Now this is actually the same as the removal algorithm we do. We're just sort of doing a bunch of swaps. Implementationally, I think it's faster if we don't swap, if we simply like leave it as sort of like an empty spot and temporarily store the 2, temporarily store the 2 in place, and then simply sort of find the right place for it. But if it's easier for you to implement, then do it with a swap. I think it's faster if you don't. Okay, I think it's faster if you just leave this an empty spot and then just do this. So can I put the 2 there? The answer is still no. 6 is higher priority, so move the 6 up. And then now this is a leaf node, so of course you can take the value, put it in, and we're done. And that gave us our first element in our sorted array. Okay, now we do one more remove. So if we remove again, what happens next? Well, 7 is removed, right? So the 7 gets removed. And so we take the 1, okay, put it aside. So remember that effectively this is sort of the algorithm, right? And then we move the 7 into that spot. Now, what does this do? Well, this is effectively our current tree. Our current tree says, okay, our current heap. Our heap goes from 0 all the way to 5. Everything after that, that's not part of the heap anymore. So our heap only goes up to here. The rest of this is part of my sorted array. I just have to find a new home for 1. I can't put it at the root, so I pull up the higher priority child, which is 6. Okay. Now, I can't put 1 into there because 2 is higher priority. So I move the 2 up. And now I put the 1 into the empty spot and I'm done. And as you can see, as I pulled it off, I ended up having a sorted array in the back. So the next number I pull will be 6. And I again put it basically where the 1 was, and that goes into the right place. And then the next number I pull off will be the 5, and it will go where the where this into this element. As I destroy my heap, I release space that I need for the sorted array in the back. That's how this works. Okay. So that's pretty much it. So if you keep doing this over and over, you will end up with a sorted array. That's heap sort. Okay. And that's everything. Thanks, everyone.